All right, good afternoon, everyone. Thank you for joining my session. Today, we're going to learn how to identify issues with app startup time. Now, most of us have always heard about frequent discussions in the community, like the app startup time is slow, and a lot of developers complain about multiple issues in their code base. I wish it was an exact science in capturing all the issues in your code base, but unfortunately, it's not. So we have certain tools or practices, which I'm going to talk about in my entire session. And then we're going to learn how to leverage those in getting those ideas and where to look upon in order to find issues about app startup. First things first, who am I? My name is Sagar Das. I work as a staff Android engineer in Vivint Smart Home. I work in the platforms team, so I work fair share of my time dealing with performance engineering stuff. I'm also a Google Developer Group organizer in Boston, so I have my own meetup running. So I like meeting up with community and other developers like you. And yeah, here's a quick look on the agenda. So we're going to discuss about the types of startup. There are multiple types of startups. So if someone says that your app startup time is slow, it can mean different things. We're going to look into what are the different stages involved in your Android app startup. We're going to talk about what are the key metrics and what are the common bottlenecks. And also we'll be wrapping up the session by talking about some of the tools that you can use for identifying issues with your app startup time. All right, let me do a quick check. How many of you present over here have at least heard the app on which you are working that the startup time is slow? Any complaints? Yeah, I've been there. I feel like every app out there has at least one scenario where the startup time is slow. Even though you have fixed most of the issues, there would be some scenario uncovered by either the QA team or the end customers itself where you will find oh my God, this is that one scenario which I wish I could have taken care of. Anyways, so what are some of the effects of slow startup time? Obvious user experience with, especially this is applicable for Zen Z and Zen Alpha who have very short attention span. And with Android specifically in Play Store, you would have at least 20 different alternatives for your particular app. So if your app takes forever to load, especially younger audience, gonna lose their interest and they're gonna jump onto another app, which in turn is going to affect your business metrics, something like user engagement and retention, things those are important for product managers, and eventually they're going to deteriorate your business growth. And ultimately, App Store ranking. Studies show that users tend to provide lower star rating or write a review in your Play Store when they are frustrated versus happiness. That's perhaps human psychology. All right, now let's understand what are the different types of startup are there. The very first one is cold startup. What that means is your app was never launched in the device, meaning probably it's a fresh boot on the device, and then none of the process related stuff ever existed in the device, and the user clicked on the app icon from the app drawer. And that is what we called as a cold startup. Now, this is the startup where the OS does most of the work in bringing your app to the foreground and making it representable to the user. So let's take a look at what are the different types of steps or the stages involved in a cold startup. Now, the very first thing the Android OS does is it creates an instance of your application, or it's called the application object creation. What it does is it's kind of responsible for managing the app's lifecycle and providing global resources. For example, in your code base, if you're gonna set up multiple things, let's say for detecting memory leaks, you're gonna use Leak Canary. Probably you're using some third-party logging libraries and all of those initialization stuff which you want all of your feature screens to be accessible with. You're gonna do it inside your application object instance. The next thing what the OS does is creates the main thread itself. The main thread is responsible for rendering the UI of the app. That's common knowledge. You do all of your resource-intensive operations in your background threads and the UI operations on the main thread. Third thing what it does is it actually creates the main activity or the actual launcher activity defined in your code-based manifest. So calling the onCreate lifecycle call and all of those things. Fourth is view inflation, or in Compose terms, we call it like the composition, the first ever composition created by the Compose runtime. So what happens in this phase is individual view objects in the XML files are created, or the composables in your screen enter into the first composition stage. The fifth step is called laying out the screen. Now, what that exactly means is uh, the OS or the system takes all of those XML views which were inflated, or the composables which were rendered, and it measures the screen and adds them into a kind of like hierarchy of view objects. And the last step is what we call as initial draw, which means the very first frame that gets rendered and it is visible to the user. So if someone asks you like how to define startup time, now this is a very loose definition. Saying startup time has like multiple meanings. Now we're gonna see like there are two different metrics how we can measure startup time in the next few slides. So if I were to loosely define startup time, I would define as the time when the user launches the app till the time it becomes visible to the user. Now, some developers out there might argue that startup time is defined from the time where the user launches the app till the app is become ready for the user to interact. That differs from business case to business case. We're gonna find out like how we can differentiate between two in the next slides. So here's a visual representation of what I talked about in the previous steps. Now, this visual representation is important in order to identify the warm and hot startup, which I'm going to talk about. So pretty much the same thing. At the base level, we have the application process, inside which the app object gets initiated, inside which we have the main thread instance, and then we have activity lifecycle methods like activity creation, layout inflation, and it ends with the initial draw. Let's move along to the second type of startup that's called a warm startup. Now, this is the most, I would say, the inexact way of defining or finding issues, because even if you refer like official Google developer documentation as of today, the way how they define is like some sort of residue already exists for the app in your device memory. So what that means is, let's say the end user launches the app and then backs out and then relaunches it again. So what happens is internally, the operating system might have created a process. That means like a process ID might have already been assigned to your app. And then the second time when user launches the app, all the operating system does is it recreates the activity stack or the main thread. So the process ID does not need to be recreated again. That's one of the instance. And second example would be, for example, if you're using like a very low-end device and the operating system decides to kill your app due to like lacking resources in memory, and then at a future point, a user decides to relaunch your app. At that case as well, the operating system would have some sort of like process residue or remnant residing in the memory, which can be leveraged for the warm launch. Now, in a visual representation, it will look something like this. You have an application process existing. The application object was already initialized and present in the memory. All the operating system does is bring forth the operation related to main thread launch and activity creation, layout inflation, and stuff like that. So compared to cold startup, the amount of time done by the operating system is definitely less as compared to cold startup, because cold startup is like initializing everything from scratch. And then the third type of startup is called a hot startup, in which all the system does is brings your app to the foreground, meaning the app is up and running, the user simply sends it back to the background, or in other words, minimizes it or restores it. And that's what like hot startup is gonna look like. And here's a visual representation of it. You have everything existing over there, application process, main thread, and all the OS does is like swaps between those activity lifecycle methods. If you send it to background, it will be on stop. And once you bring it to foreground, it's gonna start with on start, followed by I think on resume, and so on. All right, now let's talk about some of the key metrics. So let's see. When someone says that app startup is slow, your business might define one particular value, businesses are like really stringent and they prefer to have like few milliseconds. Like an ideal definition of a quick startup would be like 100 milliseconds, but not as per like Google Play Console Android Vitals. Now these are the measurements which is provided by Android app vital sections in Play Console. If a cold start is more than 5 seconds and a warm start is more than 2 seconds and a hot start is more than 1.5 seconds, it officially gets registered as a slow starter. Now, earlier I mentioned the term startup and the definition is debatable. Few developers call it as like the time until which the very first frame is visible to the user versus like when your app is ready to be used by the user. Now, there are official terms distinguishing those two cases. The first term is TTID, time to initial display, nothing but the time taken to render the very first frame in your app. And the other end of the spectrum talks about TTFD, time to full display, which is more about like your app has completely finished rendering all of those frames. And let's say like you show like a loading icon, and then you are doing a lot of like background operations, fetching resources from the network, and then showing a list of data to the user. That is going to be considered as time to full display because you're making your app ready to be used by the user. But here's the thing, studies like there are a lot of studies. I did not have like a particular studies, like you can Google it right away. So whenever you are talking about like user retention or like business metrics, time to initial display matters more than time to full display, because time to initial display is the first visual feedback your user receives from your app. If even if your app is taking like forever to load information from the internet, like downloading from internet using background threads, it's always wise to provide some sort of like visual feedback to the user, maybe a loading screen or maybe a small message, or maybe like already the data which you have already cached offline. So that would be considered as the very first visual feedback which your user receives, and that they know that the like things are coming, like things are being happening behind the scenes, and they do not have to abandon the app. Now, we're going to talk about like how to measure all of these time to initial display and time to full display. For time to initial display, we do not have to do anything, because starting from like, I think it was Android 4.4, API level 19, the Android SDK or the OS takes care of like displaying the TTID timing in the logcat. So if you have an Android app targeted for SDK 19 or above, this very day, if you launch the app and you check the logcat in your Android Studio, you're gonna see something like Activity Manager and displayed, and it's gonna show you the package name of your app followed by startup timing, which I think is, yeah, it's seconds and milliseconds. And this is the time to initial display. So I'm gonna talk about time to full display in a while when we are talking about tools to measure, because there is no direct way of measuring time to full display. Now, there is an API called like report fully drawn, but that usage may not be like advised for someone who is just getting started into like performance engineering. So performance engineering is like very, I would say like less catered to subject in the community. And I was like conscious about like, if I were to present this presentation to beginners, like what sort of tools make sense in like a very macro level outlook. So let's talk about the common bottlenecks, and then we'll be moving along like to use the tools and how to identify the issues. So one of the obvious bottleneck is heavy initialization of the main thread, loading large amounts of data, like performing slow network requests, parsing large amount of data, initializing complex data, depending upon if your type of application, especially if you are building like a game app or something, or probably like you are trying to render a 3D model. So doing all of those operations in the main thread definitely affects it completely, because main thread is reserved for like all of those UI operations. Second is, yeah, excessive CPU and memory usage. Now there are definitely like predefined SDK APIs or like SDK methods which are available in order to check the amount of CPU or RAM available to your Android device. So this is more of like, so every app is assigned with like a predefined set of memory allocated to it, depending upon the type of operating system. Now, if I'm not mistaken, I think it varies from OS to OS, depending upon like whether you're on custom ROM or you're like on Samsung OS or something. I think it would be between 24, 32, or 64 MB, depending upon the type of customization done on your Android operating system. So if your app is trying to uh, initialize a lot of objects more than that limit, then an out-of-memory error would be caused, and that's when the operating system boots your app out of the memory. And the third most commonly observed bottleneck out there is the layout inflation. Now, this is particularly applicable if you are still using like XML layouts. Now, it goes without saying, like most of the community has started using Compose in the new feature development, but when it comes to like legacy code base, we are still using XML files, especially if like your startup screen, if you're working on like a code base which has been around for like 10 years or so, there's a high chance your startup screen is still in XML. So the layout inflation can be affecting startup time, provided you're using a lot of nested XML hierarchies, like you have multiple nested constraint layouts or multiple nested relative layouts, and that just causes the operating system or the app to spend most of its time in rendering that actual XML tree. All right, now let's move along to the tools for identifying issues. Now, I mentioned this in the beginning of the talk, like identifying issues with your app startup time is an inexact science. I wish it was exact, but there are like definitely few guidelines which you can use. Now, I'm gonna talk about 3 tools which I have used, which has helped me personally in my work or passion projects, or just like working for the community and stuff like that. So let's start with strict mode. So a strict mode is an inbuilt developer tool that detects violation of certain Android development best practices. What that means is when Google created Android SDK, and it's not just Google, like any company which creates an SDK for development, they intend you to use their SDK libraries in a certain way. And if you violate that, then there should be some sort of penalty, because there is no saying what would be the outcome if you do not use the library as intended. So strict mode is a developer tool which comes bundled with the Android SDK that can help you identifying like disk and network access on the main thread, leaked resources, unsafe operations. And then when a strict mode is detected in your app, you have like multiple ways of notifying your developer. So something to keep in mind is like strict mode violation should not be visible to your user. It's more of like a developer tool. So how do you leverage that tool in within your development team? Now I mentioned that I work in platforms team, but I also have to coordinate with developers or engineers working in the feature team. Now there is no telling how and when engineers and feature team might be using a non-SDK compliant way of Android programming. So in order to prevent that, we use strict mode. And here's how the code for strict mode looks like. So inside your application class, you're gonna definitely use strict mode in your debug variant of your app. You do not want to show your like violations or all of those things to your end customers. And here's how the code looks like. So you're gonna check for a thread policy. Now, yeah, I forgot to mention that strict mode has like 2 different policies on which it can monitor. There's a VM policy and there's a thread policy. VM policy is more of like applicable for virtual machine stuff, and it is kind of not relevant for this talk, but considering this talk is about like identifying startup time issues, and it has to deal with like main thread stuff and all of those things. So that's why thread policy is more applicable over here. So the detect all call detects all kind of policy violations, whether it is like disk operations, if you are performing like writing something on the disk or to a file on the main thread, and all of those things. And then there are like different ways how you can notify your developers whenever this violation occurs. The first way is penalty log. A logcat reports all that violation on the log. Sorry, the Android Studio ID reports the violation on the logcat, and the violation will look something like this. For example, if there is like a disk write violation, they're gonna clearly see like strict mode policy violation, and then it's gonna show you the line number of your file where the violation is occurring. There is a second level of penalty, which is called penalty dialogue, and few engineers find it irritating, especially few engineers if they are working in feature team and they do not really are aware of like platform stuff. They're gonna find it like really irritating. Like, why does this dialogue keep on flashing? Now, there is a third level of penalty, which is called penalty death, which means like the app will crash every single time a feature developer engineer or any sort of engineer is trying to use a non-SDK compliant form of code. Now, few organizations do that who are like absolutely stringent about code quality. They do penalty death. But in my experience, penalty dialog works because you do not want the app to crash right away. So it's better to just give a warning to other engineers like, hey, this is not the way how this should be done, and you should be probably be checking. Okay, now the second tool which I personally like is the benchmark testing. Now, benchmark or the official Jetpack benchmark library is a way to inspect and monitor the performance of your application. Uh, Once you have like a set of benchmark test suite, now benchmark testing is nothing but like a set of test cases, just like you write your JUnit test cases or like Roboelectric test cases. There are another like test suite which you can execute regularly to analyze and debug performance problems. And it comes in handy if you can configure your Jenkins or other deployment pipeline to run all of these test cases every single feature release or maybe nightly release or production release to monitor like how your startup time has been like deteriorating over a course of time. So there are two types of benchmarking test cases. First one is macro benchmark, and second one is the micro benchmark. Macro benchmark library measures like large end user interactions like startup time, interacting with the UI and animations. Um, so that library also provides you control over the performance environment in which you are testing. That comes through like creating emulator devices and restricting the resources available to your device. And then the other end of the spectrum is micro benchmark test case, which is designed to test your code in isolation. For example, if you have like a really complex code, let's talk about the initializing 3D model during app initialization example once again. So if you want to just isolate the lines of code in which you are actually reading a 3D mesh file stored in your disk or an external storage and trying to load it in your screen, you can isolate that particular method or identify that particular method and use it in a micro benchmark test case in order to see like how much time is being taken to perform just that one task, and versus like macro benchmark is going to give you like an overall measurement of your app startup time. Okay, I think this was announced in Google I/O, but starting from like last month, benchmark has been considered as an official module in Android SDK. So all you have to do is like click on new and select new module, and then you're gonna see a benchmark type over here. You're gonna select your module name, and then on the top section, you can see like there is a benchmark module type, macro benchmark and micro benchmark. So for the purpose of this talk, we're gonna focus on macro benchmark. And this is how a typical macro benchmark test case looks like. So there are various ways of writing a macro benchmark test case or a JUnit test case, if you will. This is the way which I have tried it out, and it works for my case. So Jetpack macro bench mark library provides you by certain like by default rules, which is defined with that annotation at get rule, and we are defining a default macro benchmark rule. We are creating an abstract class called base startup benchmark, which takes a value called a startup mode. Now that is important because that is the way how we will be identifying between a cold, a warm, and a hot startup. And all of these values are provided by the SDK by default. And then we are creating at test annotation, that is the actual test case which we'll be executing. It's called the startup, and then it measures repeated, and iterations is important. So iterations is how many times you want to execute your test case. That means like every single time your app is going to be launched, and then your results are going to be shown as like minimum, median, and maximum. And then you're gonna compare like if your app startup time is 1.5 second for just one iteration, it does not mean that it would be the same measurement for the next iteration as well. And that's what the iteration values measure over here. And then this portion of the code shows how we are leveraging base startup benchmark over here, and how we are passing our arguments like startup mode cold, warm, and hot. And what it does, when we execute the startup test case over here, it's gonna execute like in 3 different modes for cold, warm, and hot, and is gonna give us results something similar to this. And this is where how we can measure time to full display and time to initial display. I told like earlier, there is a API call called report fully drawn, but in my experience, I have not found that reliable because it leaves up to the developer's judgment in order to where to use that call. And sometimes as developers, we can make mistakes, but this is what is part of the benchmark library itself. So we can find these results reliable because the library or the framework underneath it takes care of the time to initial display and time to full display. Since I had used like 3 iterations, okay, so even though my code said 3 iterations, I have executed it for 4 iterations, so that's my bad. But yeah, you get the gist, and you get like measurements for like minimum, median, and max. And there's an additional stuff which we can do using benchmark test cases, which comes really handy because identifying issues with app startup time is all about knowing how well the app initialization components are being done in your code base. Every app is unique, every code base is unique. Some things that worked for one particular app does not necessarily mean that particular tweak or optimization is going to work for your app as well. So, for example, here is an example of a few critical tasks. And by critical tasks, I mean, what are some of the operations that we do during app initialization? Probably like, yeah, initializing leak canary for detecting memory leaks, setting up like crash reporting and tracking tools. If you're using Firebase, then definitely you will be doing it before the initialization of your main activity. Setting up dependency injection, very important. Like if your dependency injection is not well set up in your app, it is going to take a major chunk of your app initialization time. Restoring downloads or data, meaning like if you want to show some like pre-downloaded data to the user. Rendering list is actually when all of your initialization tasks has been done, and then you want to show the final list of data to your user. So in order to identify a critical task and measure it as part of benchmark test cases, Android SDK also provides us another mean, and that is through leveraging traces. So trace is actually a set of like exact work or the details which is being done in your device at one particular point of time. So for example, if you are rendering a list using recycler view, and here's an example recycler view adapter, what you can do is we can wrap a particular call or a block of code within a trace instance. And if I were to write a macro benchmark test case targeting to this particular screen, in the results section, alongside with the startup time, you're going to see how much time it took for rendering or performing this particular action. Like how much time it took for creating a view holder, how much time it took for binding a view holder. The similar logic is applicable for compose as well, like how much time it took for the first composition, or probably like if you are using like multiple recomposition states and everything, you can like wrap it up with like trace points, and your benchmarking library will take care of like including the measurement in your startup results. The third and one of my favorite topics or the tools is Profiler. And we'll be talking about specifically about CPU Profiler in this talk. Now, CPU Profiler is something that comes bundled with Android Studio. It's a tool that analyzes performance. By profiling, it actually means how much stress your app undertook during a particular instance of time when you were observing its operation. So it's more of like monitoring the CPU activity, how the device was busy in performing different operations during the startup or in general, like performing any set of operation. So type of information which we can get using CPU Profiler would be the number of method calls, the amount of time spent in each method, the number of CPU cycles used, and all of those things. For the purpose of this talk, I'm gonna show like few examples of like CPU profiler charts and flame charts. And I have used like Firefox open source app, which is also known as Phoenix. It's one of my favorite open source apps out there because it's so, I feel like it's one of the only open source app which is like of production scales with like 100 million plus users, which we can use in order to learn like tons of stuff. Now, the traditional way of launching a CPU profiler would be like to you go to run and profile the app, but that particular operation or that particular instance will not be valid for app startup time. Because what happens is when you launch the app and then you spend time in launching CPU profiler from Android Studio, you miss that time frame. Ideally, you want to know what goes on during app launch and not what happens after launch. So in order to overcome that thing, so there is a way how we can do it. So we can, inside Android Studio, we can go to run and edit configurations. And there would be a tab called profiling. And we can enable the checkbox called start this recording on startup. And then we're gonna monitor the CPU activity. Now there are multiple values which you can see in this drop down, but personally I have always tried Java Kotlin method sample legacy, not the modern one. Personally, I find the other ones confusing, but I feel the Java or Kotlin method sample legacy one still relevant and something which we can use in order to understand the call charts or the flame charts. Yeah, there are three things which I would recommend to everyone before indulging themselves in like CPU profiler. I would recommend everyone to use like a really high-end system like an M1 Mac with at least 64 gigs of RAM. It's definitely helpful if you're using a large monitor. See, profiler charts are not meant to be studied or analyzed in a laptop screen. For the purpose of this talk, I have actually divided a profiler chart into like multiple sections because profiler charts are like endlessly scrollable. You can scroll up and down, left and right. And if you're a beginner, it would be like really overwhelming and you'll find like really kind of lost and lose all the motivation. And third is you need to be immensely patient in order to understand profiler charts. So I'm gonna do my best in dividing profiler charts into like different sections so that after this talk, you can like start like initial analyzing or learning further. So once we launch an app trace and then we stop a trace, the result is gonna look something like this. You're gonna see a lot of like calls to all of the methods that is being recorded in your device operation. So before we even start looking into the different types of device operation, we need to understand what sort of color representation this is. So in a call chart, anything that is green, that means like it's a call to app's own methods. Anything that is in orange, that's called to system API, and anything that is called to third-party API, including Java APIs, that's represented in blue. And that's what it is shown in this screen. There would be like multiple threads recorded in your CPU profiler, but for startup time, we are just interested in the main thread. So over here, we can expand the main thread and we're gonna analyze that. There is an option for flame chart over here, which we're gonna talk in just a moment. Now, a profiler call stack can be divided into three different sections. Now it is endlessly scrollable, but you gotta know like which methods you need to focus on in order to find something relevant. So number one is a handling bind application, which resembles when your actual application object is being created. Uh, you see call over here, and then over here in the green, this is the example from the Firefox open source app. It shows the onCreate method, and then beneath it you see all of the individual operations that is being called. So inside the code base, the Firefox open code base, they do like setting up leak canary, restoring downloads, initializing glean and whatnot inside all of their application class. The second section, which you're gonna be interested in analyzing a profiler chart, would be the section which says when an activity is created. And we can identify it through transaction executor.execute, which actually talks about like when your activity stack is being initialized and when your main activity is being created for your app. So over here, I have marked with like these red arrows, which signify the transaction executor execute call and the on create calls, which is applicable for the Firefox app. And the third part of your profiler chart would be the view traversal, which is the part where the framework actually performs the first measure, layout, and draw. And this is where the initial draw phase happens. So now this particular thing would be like a bit longer than compared to like other sections, meaning like you have to scroll way below down in order to find what is going on in your app. But here's a look on like how it looks like on XML screens and how it looks in Compose. So the only difference is in Compose, you're gonna see like the Compose UI and the runtime being rendered versus like in XML, it is going to be frame layout on measure and stuff like that. And once you scroll way below down, you're gonna see like calls to your the methods which are applicable to your particular app. And here's an example of like how that call will look like in a Compose. I took the screenshot from one of the popular Compose sample apps, Jet Snack from Google. Same thing, like in View Traversal, you scroll down and you're gonna find composition local provider, and then you're gonna see like Jet Snack, bottom layout, navigation, and whatnot. Now I mentioned about flame charts, which is the traditional way of like visualizing CPU activity. The call chart which we saw earlier, this is like something which is optimized for Android Studio. You can diagnose your startup time issues either way. Like you can diagnose it using the call charts or flame charts. Personally, I find flame charts to be more beneficial. Now, a flame chart is represented with three colors: yellow, orange, and red. Uh, how we identify like which operations in your code takes most of the time is denoted by the length of a particular block. If we were to analyze a particular flame chart, the width of each bar represents the amount of time the function spent on executing, and the entire stack represents whatever the sub operations on which it was waiting upon. So here's an example of how Firefox open source app on create phase looks like in flame chart. It is kind of reversed. In CPU call stack, it was more of like a top to bottom approach, but in flame stack, it is actually bottom to top approach. So you see on create method over here, and then you see all of those individual operations which are being initialized over here. So as an engineer, you would be interested to observe all of these width of these particular bars. Now, when you hover over the cursor of one of these bars, you're gonna see the amount of time taken for each of these operations. And then there would be options like if you right click on it, you're gonna click on like jump to source, and you're gonna take you to that actual line of code which is impacting the flame chart. And that is how you can make like further analysis or further studies like this particular operation in your startup queue is attributing to the most of the duration of it. Here are some of the resources which I would recommend. All of these are like official Android developer resources, like the launch time, strict mode, benchmarking overview, CPU profiler, and whatnot. Yeah, that was my content. I have got like 1 minute. Any questions?